This is page 1 of the Digital Logic Design Test 2 answers from fall of 2010. So page 1 begins with fill in the blank. A blank is a product term obtained by combining the maximum number possible number of adjacent squares in the map. So this has to do with our implicants, right? On our K map, which would be like such. Prime implicant, or let me do this, for example. The prime implicant would be the maximum number of pairs that you can make, which in this case is 2. That is your prime implicant. Your essential prime implicant is the amount of necessary squares. In this case, the answer would still be 2. But in a situation where like there was 1, 1, 1, 1, you would have 3 prime implicants, but technically you could have the complete circuit with just these 2 pairings. That would be your essential prime implicant. But in this case, it's just asking for the prime implicant. All right. An unspecified minterm of a function are called blank condition. So unspecified, that means we don't know if it's a 1 or a 0. Now, the only thing that acts this way, right, where we can treat it as either a 1 or a 0, is our x, or our don't care condition. Now, the dual operation of something is sort of like the complement, right? The complement of an operation. And, when you have xy and you take its complement, you get x plus y. Now, this is just the AND gate with a little OR symbol, or with a not symbol. And so the complement of the AND gate is the OR gate. So in this case, the NOR operation would be the dual of the NAND operation. Now, a combinational circuit that forms the arithmetic sum of 3 bits, that's going to be your full adder. And a full adder typically looks a little something like this, where you have 2 inputs from above, a carry, which carries over, outputs a sum, and outputs a sum. Sometimes I believe you can also have your V, which is over something, but that's what a full adder looks like. A blank is a combinational circuit that selects binary information from one of many input lines and directs it to a single output line. So that is a multiplexer. And that circuit looks sort of like this. You would have some like 2 to the 2 times 4n, something like that. But you'll note you have multiple inputs and 1 output for your multiplexer. Sometimes you also have a control of some kind, and that's your control line down here. Now this requires us to both simplify this function and implement it with two level NOR gates. So we'll begin by simplifying the function. For this, you could use Boolean algebra in theory, but because of the fact we want to get this section later on, I'm going to start with a K-map. So the K-map for this will be a 4-variable K-map. My handwriting. And I'm assuming that everyone watching this knows how to set up a K-map. Okay. So setting this up, we need a 1 wherever W is active and X is inactive or its complement. That'll be this row. And then where Y is inactive and Z is inactive, that will be this row. And then when W is inactive, or W's prime, Y is active and Z is inactive. That'll be these two in this corner. Because here W is active. That is W's zone. So we have this, we have our ones, we have our zeros. And so for the sake of simplifying this function is equal to, we will get our essential prime implicants. So let me quickly grab our essential prime implicants. Oh, forgive me. And that means that this is equal to Wx prime plus yz prime plus, and now here, this is extended a little bit. So we'll look for our dependent and independent. Z stays the same. W stays the same. X changes and Y changes. So those two variables are independent of this pair, meaning they are not related to it. So the only things that we're relying on are the values of W and Z. So W prime, Z prime. But we want to find our complements, right? Because we're trying to get two levels for this gate. We need to go through two tiers on our circuit. And a level is every column on a circuit board. So despite having many operations occurring here, this is still only a 2-level gate right here. So what we'll do is we will grab, to help get our variables, we will grab the complement of this function, the first complement of it. So we'll make a pairing of our zeros. And of course, as you should hopefully know, pairs can only be done in multiples of 2, or in powers of 2. And you want to maximize the size of your pair. So we will not grab a 1 there. We will in fact grab a pair of 2. So our f prime, in red, our f prime is going to be equal to w prime z plus our x z plus this final pairing over here of wxy. From there, we will take the second. We will get a second complement. And I'll go back to red for this. And so we will take the complement of the entire function, which will get us we'll first change our operations to multiplication. And then we distribute inside. Now, at this point, the reason we've done this is we have taken the complement of our function twice, meaning these variables, when put through, and the way that we have done it, right, where they're all ors, when we put this through 2 layers of not gates, of NOR gates, it will revert back to the original uncomplemented function. So that means we just take these variables. And this has gotten us back to our function. Now, that may be hard to believe. Here is a page where I have worked out all the details of how that works. I messed up a little bit of my algebra here. Ignore this. This expression is supposed to be here. I then used a K-map to simplify this expression over here. And it became equal to, it simplified down where both functions were equal to one another. using Boolean algebra. And so with that, you have simplified the function and implemented it with a 2-level NOR gate. And that concludes page 1 of the Digital Logic Design Test 2 in fall 2020. Alrighty. This is page 2 of test 2 from fall 2010 for the Digital Logic Design class at UAH. So, question 7. Design a code converter that converts a decimal digit from the 84 -2 -1 code to BCD. You do not have to draw a circuit diagram. So, the textbook does a really bad job of explaining this section from what I've seen. So I'll do my best to explain. I know how to answer it. And what it kind of is if you look at this, right? This is kind of like our own language, or not language, number system. If you think about binary, right? In binary, you have, we'll do 4 bits, right? But these all represent a number in decimal, right? Or these all represent like a value. So this would be 1. This would be 2 for, powers of 2. And so you can create numbers with that. This is a very similar system. In fact, you'll note it's very similar aside from these 2 negatives here. And so the way this works is by this new system, this BCD or whatever, we can create numbers from 0 to 9 using assignment of those slots to 8, 4, -2, -1 rather than 8, 4, 2, 1. You'll see what I mean in a moment. If we go decimal digit, oh, let me decimal digit. I don't know why the pen glitches out like that sometimes. Decimal digit, and then let's see. 8, 4, -2, -1, A, B, C, D, and then we'll have our conversion to binary. So W, X, Y, Z. Oh shit, did not mean to do that. Okay, so 0, 1, 2, 3. Then for ease of readability, 4, 5, 6, 7, C, 8, and 9. I clean this up because we'll need plenty of room later for the K maps that we'll write for the W, X, Y, and Z. So now let's figure out how to make this system fit these. So we don't need any of these numbers to get 0. That's going to be 0, 0, 0, 0. Representing the decimal digit in binary, it's the same thing. 0, 0, 0, 0, 0. Okay. Then you have 1. We can get 1 by 4 is our smallest possible positive. And then we have to take 2 away from that. That becomes 2. And then 1 away from that, and that becomes 1. That is represented in standard binary like that. 2, similar situation. 8 is too large. 4 is our smallest possible positive integer. -2 brings us to 2, and -1 is not necessary. See, binary 3 is going to be as simple as 4, but -2 is too large of a negative. So we're going to skip over that and just take -1. That gets us to 3. And in binary, that is represented as so. 4, we have the number for that. That is, again, represented as such in binary. 5, we'll have to go to 8. Because this is a number larger than 4. We'll have to go to 8. Skip over 4. And then we need both -2 and -1, which gets us to 5. And this is 5 as well. 6, we need 8 and only -2. 7, we need 8 and only -1. For 8, we just use 8. It's going to be the same for standard binary. And then for 9, we'll have to combine both of our integers, our positive integers, because it is larger than the highest positive integer. So that will get us to 12. And then -3, by doing both -2 and -1, will get us back to 9. And then 1001 would be our 4-bit binary standard. At this point, I thought I had erased these better, I guess not. We start with our K-maps. We'll start with W. It's going to be A, B, C, D. And for the most part, this will be treated like a pretty standard, well, I guess that's not true. We'll look for the combinations, match them with their square, and then we will look at the digit or the variable we're working with to determine what goes in that slot. So 4 zeros. In this case, we're looking at W, and so that number is 0, and 0 goes in that slot. Looking at 0, 1, and there are no more AB 0, zeros. That is the last time that AB is 0, 0, meaning that all of these are going to be 0. All right, going to 01, we have a few of those. We have 4 actually. 0400 is right here. And, oh, sorry, those won't be all zeros. They'll be, if it's not represented on the K-map, that is a don't care condition. That's my apologies. So these will be X, X, X. All right, so moving on to 0, 1. 0, 1, 0, 0. We have that, and that number for W is 0. 0, 1, 0, 1. That's digit 3. That's 0 as well. 0, 1, 11. Digit 1, and that is 0 as well. 0, 1, 10. Digit 2, also 0. 1100. 1100 is not on the map. So that will be a don't care. 1101, also not on the map. The only 11, we have an 1111, and the value for W for that is 1. So 1 will go here, and an X for the last 11 slot. 1000 is 1. Then 1001 is 0, 0, 0. Now again, following our rules for K-maps, we want everyone needs a pairing, and it needs to be the largest pairing possible that we can make. So these x's will be 1s. And we can now draw our W function. Equals, let's see. This one, that would be A doesn't change, and C and D don't change, just B changes, so that would be A, C, D plus the second group. A and B are constant. Everything else changes, plus A, B. Awesome. Now we move on to our X. So for our X, we do the same thing. We draw another K-map. Quickly. There's a reason that this gets its own page dedicated to it, because all 4 of our variables are going to get one of these. And then typically afterwards, we would draw a circuit. You would draw a circuit that takes the ABCDs and the appropriate gates as determined to get your 4 functions. Because these are technically functions. The WXYZ, they are functions, they're not. In this case, you can treat them that way. So 0, 0, 0, we already know that's going to be 0 for all of our K-maps. And then don't cares for the rest. The don't cares should be consistent from what I understand for all of the K-maps, because the non-included values are going to be constant between all of the ABCDs. So 01, 0, 0 is going to be 1 for X. And 0101, 0. 0111, 0. And 0110, 0. All right. 1111 is going to be 0. And then 10000 be 0. 1001 will be 1. And 11 will be 1. And 1010 will be 1. Alrighty. is interesting. In that case, so again, creating the largest pair we can, we'll create a pair of 2 here, treating this x as a 1, and then for these ones, we'll use the other side of the K-map because you can go on both sides to create pairs of 4 for both groups of 1. Alrighty. It means that x is going to be equal to b c d prime plus b prime d plus b prime c. Alrighty. Let's see if we can squeeze in our y. A, B, C, D. One, 11, 10. Okay. Our box is a little bit smaller. Necessity. But at this point, we know the principle. So I'm going to try to speed along a little bit faster. Of course, during a test, it's going to be all panic mode. That is fine. The don't care conditions remain constant. This one, we have these nice pairs of 4, turning these don't care conditions into 1. And that will mean our y is equal to c d prime plus c prime d, which is c, then it's the XOR d, c XOR d, and then finally z, z does not need its own K-map. The reason for that is because if we look up here, you'll note, and I will do this in a different color. When d is 0, z is 0. 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Meaning that D is only reliant on, or my apologies, Z is only reliant on D. So Z equals D. And since we're not drawing the logic diagram, that should be it. You have your 4, and you have designed yourself a code converter. And that is the conclusion of page 2. This is the third page of the Digital Logic Design Test 2 from fall 2010. And this is a lot nicer after our previous page, following up with some simple K-maps, 3 variable. So we'll start with X and YZ, 0, 0, 0, 1, 11, 10, and then 0 and 1. A map is quite literally just the mappings of a truth table for ease of convenience for reading, and then, of course, the most convenient part of simplifying expressions based off of a function's dependence on variables. So we know from reading our function, we start with the first expression, x and y. When x is 1 and y is 1, then it is equal to 1 for the function. So for these two cases, it will be 1. When x prime, so when x is 0, y is 0, and z are 0 is 1. That only fits the case of one of our squares. And then when x is 0, y is 1, and z is 0, that will also be 1. Alrighty. Again, very simple. Here we have two pairs. We have two essential prime implicants. And that will give us our function. So now we can very easily say that f of x, y, z is equal to xy plus x prime z prime. Alrighty. For question 9, this is a very similar question, although this is using the, I forget the name, but it's the m sub notation for the function, which is on a truth table. It is just reading down, starting at 0 to whatever your truth table goes to. So we'll follow that principle here. Because again, as I mentioned earlier, a K-map or a variable map is just another way of laying out a truth table, meaning that it also has its own layout that represents the same notation. So 0, 0, 0, 1, 11, 10, 0, 0, 0, 1, 11, 10. That's not necessary because this is 3 variable. So used to doing 4 variable, that it's crazy when I see 3. Honestly, blessing from above, given what we just did on that previous page. Alrighty. So basically, the thing to know is m sub increases as you go to the right, and increases as you go to the right, except that 11 and 10 are swapped. So increases as you go down, let's go to the right, 11 and 10 are swapped. Meaning that here, this says 0. So this is the 0 slot, that's 1, 1, and then this one is 2, and this one is 3. And then we move down, this would be 4, which is 1, and then 5, which is 1, and then 0, 0, 4, 7, and 6 respectively. Alrighty. Now let me grab our pairs. We have a nice pair of 4 right here and a pair of 2. And those will be our essential prime implicants, which we can use to write our function. Our function x, y, z is equal to y prime plus x prime z. And that is page 2 of the test. Page 3. Page 3 of the test complete. Alrighty, this is page 4 of the Fall 2010 Test 2 for Digital Logic Design. And the instructions here are to construct a 5 to 32 line decoder with as many 2 to 4 line decoders with enable and any additional logic that you might need. And for notation purposes, the 5 to 32, 5 is your inputs, 32 is your outputs. And when you use decoders with enable, the entirety of the decoder circuit counts as one decoder by compiling a bunch of smaller decoders. So we are not having one giant 532. It's not that simple. We're actually, I guess, designing the inside of the 5 to 32. But it's not as bad as you may think. It is very similar to a truth table. For instance, in this situation, this is going to output some value from 0 to 3, basically. There's 4 possible outputs because x could be 0 and y could be 0, that's one output. Then x could be 1 and y could be 0, that's 2. x0, y1, 3, y1, x1. And then enable means that only if there is a 1 being put into the bottom of the decoder, will it be active for, will it work? Will it use that one or take input for that one and then output? So I'm going to kind of work backwards a bit here, or I guess I'm going to fill in. So let me box off this. So W equals 1. And we're going to have, again, 5 inputs. So from from D0 to D4. So we'll start with D4 out here at a 1 to 2 decoder. 2 values. And over here will be our many outputs. We need 32. So that's going to be 8 2 to 4 line decoders. So let me make it a little bit bigger. Just try to conserve space. 1, 2, 5, 6. Ooh, yikes, we're running out of room. 2, 4, 6, 7. And then finally 8. All right. These will be 2 to 4s with enable, of course. 2 to 4. And this will probably get very messy very quickly. But I will do my best. 2 to 4. All right. These will output our 32 final outputs, which we'll use an L for. I'm realizing that seems a little strange. We're using D for our inputs and L, which can very easily be mistaken for I for our outputs, but it's what we're working with here. So 0 or L32, L31, L29. Or, sorry, it wouldn't actually go to 32, it would go to 31 because we start at 0. 31. L19, 18, 16. In there. Hmm. 11. I only did 3 here on accident. 5. 4, 3, 2, 1, 0. We'll pretend that that lines up. You get the point, right? Okay. And then, so that gets us our 32. That takes 2 inputs. We'll choose our 2 inputs to be a simple D1, D0 for all of these. You'll see it's kind of coming together sort of like a truth table, right? Like when this part of the expression is right, or is 1, then when this other part of the expression is 1, yada yada, kind of compiling together of like this, we'll have one for off and on, and then all the different outputs. Yoink, draw some rudimentary lines. It's harder when the resolution on the paper is pretty small. So you convert a PDF to PNG, I know, first world problems, but alrighty. And then from there, we only have 2 more decoders to draw. They will be, because there's only 2 outputs from this, we only have 5 inputs. We've already used 3 of them. We have 2 inputs left. So let me make them a little bit bigger since we managed to save all this room actually. And that'll be D3, D2, 3, 2, 2 to 4, 2 to 4, 4 times 4. I don't know why I said 4 times 4. 4 plus 4, that's 8. That's how many we need to get 32. Because 4 times 8, 32. All right, so, and this is 0. That'll enable that. Okay. And then yoink that. Enables that. Enable there. That's what I get for squishing them together. Enable there. Boom. Enable. Oh shoot, went a little too low. Hopefully it just matters where they connect. And then that is your 4th page. That's your decoder. And that's all you need for that. Alrighty. Alrighty. Welcome to the last page of the test two for to double check. The test two for fall 2010. Yep. Now, this section, I'm going to try to remember to link it. A great geeksforgeeks.org article covered this question, and their implementation doesn't perfectly align with what my teacher wants for this answer, but it did help me get sort of a grappling on understanding exactly what's going on here. It's not perfect, but there's some pretty handy things. Typically, your selector lines are going to be log 2 of this large multiplexer here. So I got 5. This gets us how many multiplexers we're going to need in order to construct this 32 multiplexer. I will quickly write down. So this is something that you can use to calculate the total number of multiplexers only if the number of stages which is kind of like levels with the other circuit boards we've done so far. If P, which I'm not sure what P stands for, again, I highly recommend you read this article, try to understand it yourself. But if P is an nth power of Q, allows this to be a geometric series, which gets you the total number of multiplexers. And like I said, it's a geometric series. One equals n minus 1 over q minus 1. And that will get you your number of multiplexers in that situation. That was not the situation here, and that is why we're going to actually have to use with enable in order to get the amount of selectors we need, if I'm following. So similar to with the decoders, we'll have to use with enable. So we'll start with drawing our 4. For 8 ones. Because again, like I said, this is sort of the inverse of the decoder. So a lot of inputs to one output. Which I guess is kind of what the... No, that's kind of... Yeah, I'll stick by that. Yeah. So we'll draw a bunch of lines. I won't even bother doing all of the appropriate lines. This is 31. This is 0. And then the selectors that we have access to for this will be 3. So S2, S1, S0. Again, we need 5 selector lines. And so what we'll do is we'll then take one final multiplexer, right? And that will get us our last 2 selectors. So you can guess this is a 4x1. And that is that question. And so, yep. Okay. Now for a much easier question from my understanding of how this class works, or this material works. I would definitely keep in mind just log 2, 32, read that article, try to make sense of it. Keep that stuff in mind when you're in a testing environment. All right, the final question of the test. We have our table of propagation delays. And at any given level, right, we have to factor in, well, actually, we have adders. And so the adders are just kind of going to, it'll work out. So let's see. There's 0 delay on this first level. So these input, these are XOR, XOR. I can tell because of the line before the OR as such. And I draw my ORs a little bit differently than everyone else. But yeah, this line signifies that it's XOR gate. So it's going to be 80 PS. So 0 in, 80 here. But of course, it starts from this is the start, right? So, well, just read right to left for this. Now, full adders are 150 propagation delay. So this is going to be 150. And then it's an adder. So go ahead and add. We have 0 from this side, 0 from this side, 80 plus 150. That's going to get you 230. But the number is also going to carry over in the carry. So, because it has to wait for both this to finish and this to finish to then send over this information. And this adder is going to wait. This full adder is going to wait for the carry. So it will be delayed by the amount that's the first full adder delays it. So that becomes then 80, 150 plus 230. That gets you 380. Which I'm not sure I understand that math. That to me, oh, right. Because this delay no longer really counts. It's kind of null and void. Still going to write it down, but it's not going to affect the propagation delay because this is gonna, it'll send the input here and then it'll be waiting. So that means your total sum will just be the delay of the carry and the full adder. And we'll carry over to this third one. Again, same situation. 150 plus 380 is going to get you 530. And that continues to the carryover. And so now you have your C and you have your V. So 680. And for whatever reason, his key is writing 680 here. However, I am personally fairly confident that it should be 530 because it's the carry 3 value that's being input there. So I think that is a misprint on the teacher key. which honestly is pretty frequent from what I've noticed so far. And it's not to be unexpected. So say 530 and 680. But again, this one's going to finish up first and then be waiting on this. So we're only going to add 680 plus 80 rather than 530 plus 680 plus 80. And that's going to get us 760 as our final value for V. And then the carry 4 will just be our final value for carry. And that'll get us 680. All right. And that is the last page of test 2 for Intro to Digital Logic Design on the 2011 test.